Okay, so good morning to all of you, and today we will discuss the state space representation of discrete time system. State space representation of discrete time system is similar as continuous time domain. You know, in continuous time domain, state space representation is equal to x dot is equal to x plus bu. Okay, x dot is equal to x plus bu. Suppose you have one transfer function, uh, that is ys by us, and you have one transfer function dot 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 like that. So from the transfer function to state space representation, there is a four method: controllable canonical form, observable canonical form, diagonal canonical form, and Jordan canonical form. So in the similar way, state space representation of discrete time system. Suppose you have in the last class I told you that in discrete time system, that is relation between input and output represented by the difference equation. Okay, so suppose one difference equation of discrete time system is equal to yk plus uh, a1 yk minus 1 a2 yk minus 2 dot 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 an ykn minus 1 is equal to b not uk plus b1 uk minus 1 dot dot bn u and k minus 1. Okay, and what is k is the kth sampling. You know, kth sampling for the kth sampling for discrete system, and yk is the discrete output signal in the discrete form, and uk is the input in the discrete form. If you apply Z transform, then first transfer function of the given uh, uh, difference equation is equal to yz by uz is equal to b naught plus b1 z to the power minus 1 plus b2 z to the power minus 2 dot dot bn z to the power minus n divided by 1 plus a1 z to the power minus 1 dot 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 an z to the power minus 1. So if you multiply z to the power n in the both numerator and denominator, then the first transfer function of the given differential equation, that is equal to yz is by uz is equal to b naught z to the power n plus b1 z to the power n minus 1 dot dot up to bn divided by z to the power n by an z to the power minus 1 dot dot up to an. So in the similar way, just if you compare with the continuous time domain, so again a discrete time system, you can realize any discrete time system to state space representation. There is a four-way: controllable canonical form, observable canonical form, diagonal canonical form, and Jordan canonical form. Okay, so there is a four-way to represent uh, 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 any discrete system in the state space representation. So as I told you, in the continuous time domain, the representation of uh, any system in state space, there is no unique representation. Okay, so you can represent in a various way. You suppose you have one RLC circuit. So the state space representation of RLC circuit depends on the choice of state variable. Okay, so suppose I choose voltage across capacitor and current across inductor in RLC circuit, and uh, suppose another person we have choose uh, voltage drop across resistance plus voltage drop across capacitor plus voltage drop across inductor. So it depends on the choice of state variable. That is, the state space representation of any system is not a unique. It depends on the choice of state variable and form we have to represent. So there is a four-way to represent any difference equation or any first transfer function to state space. There is a controllable canonical form, observable canonical form, diagonal canonical form, and Jordan canonical form. Okay. Okay, so actually depends on our requirement. Suppose if you want to check the controllability, uh, as I discussed in the continuous time domain, what do you mean by controllability and observability? Okay, so if you want to check the controllability of state space representation, so better you have to represent the given pulse transfer function to the controllable canonical form. If you want to check the observability, so you have to better you have to represent the given system in observable canonical form. And if you want to find the uh, poles of the system or the solution of the system in terms of poles, then you can represent the system in using the diagonal canonical form and Jordan canonical form. So based on the your application, you can represent a system state space representation to controllable canonical form, observable canonical form, diagonal canonical form, and Jordan canonical form. So, now suppose you have one pulse transfer function and you want to represent a controllable canonical form. Just wait. Okay, so in the last class, I told you that from first transfer function to state expansion, there is a four-way: controllable canonical form, observable canonical form, diagonal canonical form, and the Jordan canonical form. So if you want to uh, realize a state space in a controllable canonical form, so directly you can represent, suppose you have n number of state variable, so n number of state variable depends on the order of the differential order of the first transfer function. So there is n number of poles, then we have to choose a minimum n number of state variable. So suppose we have n number of state variable x1, x2, x3 dot dot xn, and as I told you that in case of, just wait. So in case, in case of controllable, in case of discrete time system, uh, that means if you compare with the continuous time system, so in continuous time, the state space equation is equal to x dot is equal to ax plus bu. That is, you have to represent the state derivative of state variable in terms of other state variable. Okay, so in a differential equation, state space representation, that is the x1 k plus 1, x2 k plus 1, that is k plus 1, which is equivalent to derivative of the state variable. So we have to x1 k plus 1, x2 k plus 1, k plus 1 dot dot up to k plus 1. In Jordan canonical form, the that is the coefficient of denominator, that is a and a minus 1, a minus 2, have to be in the last row, and the other row is equal to 0 1 0 0 0 0 1 0 0 dot 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 in this way. And finally the coefficient of denominator, that is you have to write in the last row, that is in the minus k minus a minus an minus a n minus 1 dot dot up to a minus 1, x1k x2k dot 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 up to x1 plus 0 0 0 0 1 uk. Okay, and output equation becomes yk is equal to bn minus an b naught b n minus 1 minus a n minus 1 b1 dot 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 a b1 minus a1 b naught into x1k x2k dot dot x1k plus b naught into uk. Okay, so again the second form is called observable canonical form. So in the observable canonical form, the given first transfer function you can represent in the form of x1 k plus 1, x2 k plus 1 dot 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 up to x and k plus 1 0 0. Now the coefficient of denominator you have to write in the form of last column, that is minus a n minus 1 minus a n minus 2. Hello. Hello.
Yes,
Hello.
sir.
And the other element are 0 0 0, and last element is minus an, then 1 0 0 0 0, last element is minus a and minus 1. In this way, and the last row becomes 0 0 0 1 minus an and x1 k x2 k dot 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 x and k. And B matrix, that is Bn minus A and B naught, Bn minus 1 minus A and minus 1 B naught dot 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 up to B2 minus A2 B naught minus and B1 minus A naught B naught. And the output equation becomes 0 0 0 0 1 x1 k x2 k xn minus k xn plus B naught uk. And third form is called diagonal canonical form. So suppose you have one transfer function, a pulse transfer function. So you have to find out the poles of the system. So how can you find out the poles of the system? If you take the denominator is equal to 0, then we have n number of poles. So if the poles of the pulse transfer function are all distinct, suppose we have n number of poles p1, p2, p3 and pn, then you can represent the given pulse transfer function to the diagonal canonical form. Then the poles of the transfer function we have to write in the diagonal element. That is p1, p2, p3, p4, p5, pn minus 1, and other element is equal to 0 0 0 0 0 0 0. So and again B matrix is equal to 1 1 1 uk, and C matrix is equal to C1 C2 dot dot Cn, x1k x2k x3k xn minus k and xnk plus B naught into uk. So what do you mean by C1 C2? C1 C2, suppose you have a n number of poles. So suppose you have one number of poles. So suppose you have one transfer function yz by xz is equal to, what is the pulse transfer function? B naught into z to the power n plus b1 into z to the power n minus 1 dot dot up to b naught divided by z to the power n plus z to the power 1 plus a1 z to the power n minus 1 dot 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 up to a naught. So if you, so how many number of poles? There is n number of poles. Suppose number of poles at is equal to, or and all poles are distinct, that is p1 p2 dot dot pn. So you can write the given first transfer function in the form of partial fractions. Suppose the first vector is c1 by z minus p1 plus c2 by z minus p2 dot 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 to cn by z minus pn. So c1 c2 are the factor of each pole. So that's why the value of c1 c2 is written in the output equation and b naught into uk. And fourth form is called Jordan canonical form. Jordan canonical form. So suppose n number of poles of any transfer function among n number of poles. Suppose m number of poles are same. That means suppose let any transfer function, pulse transfer function have n number of poles, n is equal to 5, and among 5, 3 are same. Okay, so if the C are same. So in the same way, if the first transfer function involve a multiple poles of order m at z is equal to p1 and all other poles are distinct, then state equation becomes x1. So that means there is a the m number of poles are same and others, that is n minus m number of poles are distinct. Then you have to represent the given equation x1 k plus 1, x2 k plus 1, dot dot up to xm k plus 1, and the poles, that is the repeated poles p1 p2 in the diagonal elements 1 0 0 0 p1 1 0 0 0 0 p1, and you have to divide this part in the four in the matrix in the four part. First part we have to write down the same pole on the diagonal element, and we have to write other in the other part, that is in the other part we have to write 0 0 0 0, and again in this part we have to write 0 0, and in this portion the m that is from starting from the m plus 1, so m plus 1 element, the poles are written in the diagonal element, and again 0 0 1 1 0 0, and what is c1 c2 c3, so c1 c2 c3 again are the coefficient, that is the constant of the factor. So now those are the basic way how you can represent or how can you convert first transfer function to state space representation. As I told you, the state space representation are non-unique. Okay, non-unique. So same first transfer function you can represent in a different way. First way is called Jordan canonical form, second form is called observable canonical form, third form is called diagonal canonical form, and fourth form is Jordan canonical form. So details of the that is the derivation of how you can obtain the control canonical form and observable canonical form, diagonal canonical form, Jordan canonical form are given in the book. You can go through it, but it's not more important. Just we have to know the way of representation of any pulse transfer function to to different canonical form. Okay, now we have to solve one numerical. Okay, we have to solve one numerical problem number one problem. So suppose we have one pulse transfer function yz by xz is equal to z plus 1 by z square plus 1.3z plus 0.4. The state, we have to represent the given first transfer function to the state space representation in the canonical form. So find state space representation first in controllable canonical form, second one observable canonical form, and third one is diagonal canonical form. Okay, so from the given first transfer function, tell me the order of the uh, given first transfer function. Hello, what is the order of the given transfer function? Hello, I am audible to you?
Yes,
sir.
2, sir.
2. यार रिप्लाई नहीं करोगे तो हम कैसे पढ़ाएंगे? ओके, सो दैट मीन्स टोटल नंबर ऑफ स्टेट वेरिएबल कितना हो जाएगा हमारे पास? 2. ओके, सो सपोज वी हैव first state variable is x1k and second state variable is x2k. So first form is called controllable canonical form. So first we have to write x1k plus 1, x2k plus 1. Okay, is equal to G matrix x1k x2k plus B matrix into UK. Okay, now in controllable canonical form, the first row 0 1 0 0 0 0 up to xn 0 0 1, and the last row, the element of last row is equal to minus an minus 1 minus an minus 2. Okay, yes or no? That is the coefficient of denominator. Yes or no? So, hello. So, first row become 0 1 and second row first element क्या आएगा? यहाँ पे फर्स्ट ट्रांसफर फंक्शन क्या दिया हुआ था? लास्ट एलिमेंट क्या था? माइनस ए एन. उसके पहले का एलिमेंट क्या था? ए एन माइनस 1 जेड टू द पावर माइनस 1, सॉरी, इंटू जेड. यस और नो? सो यहाँ पे लास्ट एलिमेंट क्या आया था? देखो तो माइनस ए एन माइनस 1. दैट मीन्स यहाँ से पीछे के साइड से उसका कोफिशिएंट लिखे थे. यहाँ पे क्या आएगा जल्दी बताओ? What is the value of an from the given equation first transfer function? What is the value of an? Hello. So A matrix becomes minus 0.4 minus 1.3. Any doubt?
No, sir.
And next, what will be the B matrix? So from the given formula 0 0 0 1, so it becomes 0 1. Now we have to write the output equation, that is yk is equal to b and an minus b naught. So what is the value of bn? If you compare with the equation, what is the value of bn in this transfer function? What is the value of bn? Is equal to 1. And what is the value of bn minus 1? That is
1.
equal to 1. So what is the value of n in this case? So bn, that is bn is equal to 1 minus, what is the value of an? 0.4 into b naught. So 0.4 into b naught, that is equal to 1. So first element and second element, sorry. So what is the value of B naught? B naught is a coefficient of z to the power n. Yes or no? Hello. So यहाँ पर what is the value of n? Value of n is equal to 2. So A2 is equal to 0.4, A1 is equal to 1.3, and A naught is equal to 1. Similarly, B2 is equal to 1, B1 is equal to 1, and B naught, that is the coefficient of z square. So there is no z square term in numerator. That's why B naught is equal to 0. Okay, so 1 minus 0.4 into 0, and other element is equal to Bn minus 1, that is B1, 1 minus A1, value of A1 value is equal to 1.3 into 0. Okay, so its value is equal to 1, and xk, x1k, x2k plus what is the D matrix? D matrix is equal to B naught. So there is no B naught is equal to 0. So similar simple yk is equal to 1 x1k x2k. Any doubt? Just we have to compare uh, with a standard canonical form. Now next we have to write in the observable canonical form. Just wait.